Today we are going to solve Project Euler problem 49. I'm going to read out the problem statement. The arithmetic sequence 1487, 4817 and 8147, in which each of the terms increases by 3330, is unusual in two ways. First, each of the three terms are prime, and second, each of the four-digit numbers are permutations of one another. There are no increasing sequences made up of 3, 1, 2, or 3-digit primes exhibiting this property, but there is one other 4-digit increasing sequence. What 12-digit number do you form by concatenating the three terms in the sequence? Okay, so in order to solve this, I am going to create a new file, p049.hs, and I am going to define some utility functions that I am going to need. So first, we need to check all 4-digit primes. So I want to have a list that holds these primes. So 4-digit primes is a list of integers. Filter is prime 1000 up to 9999. So basically we are filtering all 4-digit numbers on their primality. This of course means that we need a function is prime. This will take an integer and return a bool. And I am just going to do this the straightforward way. So a number n is a prime if all numbers that, or if no number that is between 2 and n-1 divides it. So we check every number from 2 up to n. Actually, n-1. Actually, we don't need to check up to n-1, but it suffices to check up to the square root of n in this case. So as square root n, of course this does not work because we need to do from integral n. So we check or a number n is prime if all of these numbers when dividing n produces a remainder that is not 0. So if n mod x is not 0, then we have a prime. Okay, so, and also for convenience, and it will become clear later why I need to do this, I want to have a set that also holds all 4-digit primes. So for this we need to import qualified data.set ss 4-digit prime set and this is equal to, well, to this list 4-digit primes, but as a set. Okay, so now let's go into, oh, actually not. Actually, we need one more helper function, and this helper function will check whether or not three 4-digit integers, are permutations of one another. So I call this isPermutation or isPerm, and this will take a triple of integers and return a bool if the three integers that we get are well, permutations of each other. if they use the same digits. So is perm of number A, B, C. Let's convert this into a list A, B, C. For each of these numbers, we want to sort the digits. Then convert the numbers with sorted digits to a set. And if the set has size 1, then we know that the numbers were anagrams of each other. This works because identical elements in a set, a set can't hold duplicates, so numbers with the same digits, if the digits are sorted, are only stored once. So map sort digits, which we will define later. Make a set. And then check whether or not this set's size is equal to 1. Okay, of course I have 1 comma too much here. And now we need to define sort digits. Sort digits will receive an integer and return an integer, but with what's that? But with its digits sorted. So for example, I want to have it so that the number, let's just say 4352, will be mapped to the number 2345, because that are the same digits but ordered. Okay, we can do this. We can sort digits of an integer x by basically building a list of each digit and then calling sort on it. So in order to call sort, we need to import data.list, and in order to map, in order to get a list of the digits in a number of length 4, we will do the following. So we will perform the following calculation. So we can get the digit at position I, or let's rather say at position j, if we take x modulo 10 to the power of j, and then divide by 10 to the power of j. Minus 1, yes, minus 1, sorry. Sorry for the slight confusion here. So this will basically, in the first step, we will cut off all the numbers that come before the number we want to isolate. So x mod j to mod j to the power of 10 to the power of j. So for example, in a first step, if j starts at 1, we would calculate x modulo 10, which will give us the last digit. And then to isolate the digits after the one at the position we desire, we need to divide by j to the power of 10 to the power of j minus 1. So And then, of course, we want the digits at positions 1, 2, 3, and 4. So if you don't understand this right away, then please take a moment, think about it, go through the steps, maybe on a piece of paper or so. And then we can call sort. And of course, this returns a list of integers and not an integer. Okay. Now, why is there an error here? S.size. Of course, we need to do this. So the size of S. And this basically now completes the helper functions that we need. So let us now compute the valid combinations of 4-digit primes. I will call this method or this function valid 3 combinations, and I want to do this the following way. So I want to iterate over the list of 4-digit primes in a sort of inner and outer loop, if we were talking imperatively. And for each combination of 2 4-digit primes, we will calculate the difference. Look if we go one step further, so to speak, is there a prime or not? And if there is a prime, then we check whether or not these 3 primes, these 3 4-digit primes, are permutations of one another. So, valid for 3 combinations, of course. This will take the list of 4-digit primes that are still left to check and return a list of 3 4-digit primes. So valid 3 combinations. We get a list, and the first element of the list is the prime we are going to check. So let's do the recursive call first. So valid 3 combinations with the rest of the list, but we append all the valid 3 combinations that have X as their first element. So just to make this clear, if we have a look at our at the arithmetic sequence that is given in the problem statement, then this number, and this number would form such a free combination. And this would be the first number in the free combination. So this is why this is a tuple of 3 integers. So valid 3 combinations starting with X. Of course, we need to define this. Valid 3 combinations starting with X is can be defined in the following way. So we first check every other prime that is in the rest of the list. And we compute the difference between X and each element in XS, And then for each element, we basically perform the step onto a new number, look whether or not it is prime, and then perform the is perm check. So basically, we want to do a map such that numbers a and b, where a is basically our x. That we can do this more easily. So we map each number that are remaining, so each number in XS, we map to the tuple x, b as the second element of the free tuple, and then b plus b minus x, because we compute the difference between b and x and then go from b in this direction. Basically, this would mean in our problem statement, we set our first number to be 1487, our second number to be 4817. Then we compute the difference, which in this case is 3330, and then from that we get the third number. This way we don't need to have basically a complexity of n cubed, only of n squared. Okay, so obviously these are not valid combinations starting with x, because it might be the case that this here the third element is not prime. Okay, so we need to account for that. We need to filter these triples that we have just generated, such that each triple, we don't care about the first two elements, we already know that they are prime, but we need to check if the third element is a member of the 4-digit primes set, and this is also why we have, or why we defined this variable as a set of the 4-digit primes, because this allows us to do queries like this very efficiently. Okay, that's basically it. So now IO main method, IO main, we first generate all the valid free combinations of the 4-digit primes. Then we check or we filter these free combinations that we now know consist of primes for the fact that they are indeed permutations of one another. So filter is perm. And then we print the result. And of course, we can also do a pretty print, so that we can just copy paste the solution into the Project Euler website. So let's do this, concat tuple. So takes a tuple, outputs a string, and this is straightforward. ABC, tuple with members ABC gets mapped to show A, append show B, append show C. And then we can insert this here. Compile, the program. So GHG minus O2 OP and then run it with time. Oh no, non-exhaustive pattern. Yes, of course. That makes sense because I forgot to add the base case here. So if the list of primes that we have as an argument here is empty, then of course the list of valid combinations that we can build from that is also empty. So let's do it again. And this now gives us the correct result. You can see here the first solution that was shown in the project or in the problem description. These are the three numbers concatenated, and this is the solution we were looking for. Thanks for watching.